Introduction to Algebras of Chiral Differential Operator, Part 3.
Thank you. It's on, right?
Yeah.
All right, so finally we'll start looking at what, after all these preparations, let's finally look at an example of the real thing. So, in Algebra of Chiral Differential Operators, an example. I thought I would give you an example and do some concrete computations, exactly what stimulated an interest in the subject. And then, armed with this experience, we will try to understand it better. So, what I would like to talk about is, I think Zhu mentioned it. It's nothing but a beta gamma system. But to make stronger impression, I will call it Chiral on the line, as I would like to think of this as an analog of a simple example of what we discussed, the while algebra, globally defined differential operators on C. So what's that? So as a space is just a polynomial ring. The reason for these fine imitation is perhaps obvious. I would like to think of those as analogs of x and ddx in the usual situation, and I comment on that more later on. Now, so this is just an infinite polynomial ring on infinitely many variables. Now let me introduce the following layout. It will have the same basis. I could have used the basis will contain that as part. I could have used different letters, probably I should have. But let's minimize our notation. So an infinite basis like this. And the commutation relations are C is central. So that's, at the moment, that's just, you see. So, of course, this thing is an A module where letters that appear here act as multiplication, and letters with negative, perhaps positive indices operate. All right, probably I should give a more formal description, and then you will see what is it that I wanted to say. So I will introduce the induced representation from A plus to A of the one-dimensional module, where A plus is a subalgebra spanned by xn, dn plus 1 with n.
So
You don't
the other way around.
Ratio between xn and xn.
Say it again? Ah, except, yeah, thank you. I've looked at this so many times that, of course, I forget what's needed and what's not. And so, that's the A plus, and it operates on C in such a way that as C goes to 1, and x's and d's that are here, to 0. Now, of course, it's an immediate corollary of the Poincaré-Birkhoff-Witt, that this module is very naturally identified with what I started with. And so, chiral C of x is indeed an A module. Any questions so far?
Big puzzle about the double negation. Upstairs you wrote minus n and then n less than 0. That's what you meant.
Let me make a picture, we will see.
So it means in D, in the chiral D, the x's are positive or negative?
We'll correct in a second. It's easier to reconstruct the picture. So it's a polynomial ring. It contains, the thing is organized by levels. That will soon appear by layers, better to say, that will soon be recognized as the conformal grading. So level 0 contains only x's. Level 1, and the whole thing, of course, is a polynomial ring, so it's acted upon by its part like this. So from now on, I will not be listing them. So layers simply given by minuses, by minus subindices. So therefore, at level 1, what I want is this. At level 2, more choices, you know, x minus 2, x minus 1 squared, and 2 more. Something like this.
And also x0 is chances, as you just said.
Just as I said. So I'm listing, so what's listed is the basis of the whole thing as a C of x not much. So does it agree with what I wrote above? All right, so the point I will make is that this thing there is a vortex algebra structure. But before that, I'm trying to postpone this, the unhappy moment of introducing such thing. Before that, I would like to make a comment. So what's the reason for the notation? Is there any chance that this thing I introduced has something, however vaguely, to do with what we discussed, algebras of differential operators? I will now make a case that it does, clearly, in fact, in 2 different ways. Both are important. One of them will be more important for me later on, and one less. So, first of all, a moment's thought will convince you that this is something very naturally related to the space of Laurent series. Well, to have differential operators, you need, you know, variety. This is something infinite dimensional. The most natural way to think of it is that this is an in scheme. I'll just mention these words as they are fashionable. I won't be using them in any serious sense of this word. But by not mention them if it's so easy. So, of course, this is a union of those. That's the definition of the left-hand side. The right-hand side is naturally an honest-to-goodness scheme. In fact, whenever you think about these words, there are obvious coordinates. Look, a point, educated people would say C point of this thing, is just a Laurent series. Let me record it like this. So from this point of view, you immediately see that the collection of xn's is a coordinate system. Furthermore, in a rather obvious sense, any space like this, so for example, this thing. Look, a point is determined by infinitely many, perhaps non-zero values of xn. What it hints at is that this thing is a spectrum of a polynomial ring on infinitely many variables. Etc. The same, of course, applies to each of those. And so the whole thing is really a union of something understandable. So what are functions? So let's talk about global functions there. Again, naively. So functions on this space are, of course, polynomials in those variables. I'm doing it in the wrong place. Maybe 0, x minus 1, x minus 2, etc. So the fact that this is a union, it means that you should allow infinite series in that direction. Think about it. You will be able to evaluate whenever only finitely many positive x's are non-zero. Similarly, you can handle vector fields, something that is closer to our subject. Well, of course, it's polynomial, so you will have ddx's multiplied by global vector fields, multiplied by such functions. These, now, of course, I'm entering this complicated area of algebraic geometry, and it's not my intent to go in any depth. But it's good to see at the beginning that such sums make sense as derivations of this object if they may be infinite, but infinite only in one direction. Exactly in that direction where the functions are kind of finite. So they, so to say, summation extends to I, if I am allowed to write it like this. That means that in the negative direction, the summation is finite.
There is a minus sign.
Where?
Is that, do you want it infinite in that direction or the other direction? Given the xn is...
I think infinite in negative direction. Oh, yeah, infinite in negative. This is what you meant. Yeah, sure. All right. So infinite, I don't know. Infinite in this direction, finite in that. It doesn't matter, really. Think about it. It's no concern of me. It's just, I'm just saying that we have this, and so this gives us grounds to more or less sensibly define the ring of differential operators. And of course, there are choices here. And I'm not saying that I'm capable of telling you something of content about, say, this, the category of modules over the string, however we define it. What I am saying, though, is that what I defined here is a sensible thing. It's simply whatever this is, in the end of the day, that makes perfect sense in a rather unique manner. So that thing is a D-module of distributions supported on so to say, holomorphic on arcs. If you give this a thought, you will see that what's written there, especially here, is exactly that. But what's written there is, no matter how you define this, that really is that thing modeled the left ideal generated by functions whose zeros extract this subset. x1, x2, or rather, ideal generated by x1, x2, x3, etc. If I got things right, I've thought about it today, and I think I convinced myself that even if you pick the, so what you see, we've got there something reasonably small. It's only polynomial, for example, in these in the negative direction, and all the polynomial in x's in the negative direction. And this is what those vector fields should actually satisfy. Remember, this is the second appearance. The reason this is a space of distribution supported there is something I explained last time. You see, any differential operator for the purposes like this you can write as a monomial in D times a monomial in X's. This condition will show you that the result is just a space of monomials in negative D's and positive X's. And that's exactly what happens. That's how we discussed that, remember? We discussed exactly this situation when submanifold was a point in one-dimensional space. That's exactly what we obtained. Any questions? So, we've got a D-module of distributions supported on semi-infinite, so to say, half-dimensional subspace of a certain name. This is a nice relation to D-modules, but of course it gives you no hint why this thing carries any kind of algebraic structure. And indeed, we all know from our college days that there's no natural way to multiply distributions. So this doesn't clarify the Vortex Algebra structure at all. However, there is a series of well-known papers by Kapranov and Vasserot when precisely this issue is addressed. They make sense of this thing. This is a rather non-trivial algebraic geometry question, so they define it, and then they show that a thing divided by words like that sometimes carry a structure of a Vortex algebra. That's remark one. Any questions?
Yeah, one question. So the picture circle with dot inside. So somehow, are you saying that this is a limiting case? Kind of limiting case.
What is limiting case?
The algebraic structure you're describing now is kind of limiting case of yesterday's talk. Somehow we're taking rid of that picture.
Well, it's distributions. The last time we never focused on distributions, so it's not quite the limiting case. So that's one, and that's very important, but that's not what I will be concerned about. Here is another, which closely related but different. really different, and which is more related to what I'm planning to.
Why that dct over dct x minus 2 to 3 does not contain only half of the derivations?
Sorry, that's a mistake. So what I described, so I should have described, I should have killed half of derivations, and I forgot. So you always get the module supported there if you kill these variables. And Kashivara's theorem says that this is going to be at least in finite dimensions. It's going to be the direct image of a certain D-module living on this subspace. But what D-module we are talking about? In this case, I was talking about the D-module of functions, meaning that in this terminology, I should have killed exactly the D's I should have that aren't there. So D0, D1, D2, etc. Indeed, to get an O module, you kill differentials on the right because they kill the unit that generates the O module. So for a subspace, we kill those, and for the outer space, we kill the annihilating area. Thank you so much. The second remark is kind of more to the point. This particular space as follows from that.
No, I'm completely puzzled. If you kill x1, you also kill del1, and you also kill the commutator, so you kill the unit.
That's an abelian subalgebra. Unless I made a mistake, I killed an abelian subalgebra. X1, etc. denote D1.
Sorry, I minus sorry.
And it's a maximal abelian. So, for example, if you attempt to add D minus, then indeed this phenomenon you mentioned will occur. We are not allowed to do that. All right, now to the space itself. So that's polynomials. Let me skip writing. What I wanted to say now is that, at least in this, well, it's an explicit case. So this is nothing but the space of functions on jets in the cotangent bundle to C. I don't want to talk about the definition of jet scheme, but in this particular case, it's especially easy. So going from a flat space to jets means really have each variable spawn a collection. 0, 1, 2. And in addition, you typically have a derivation that sends ui to ui plus 1, something like this. I probably should have changed the index, but that's the typical structure of a jet. Now, why is this important? Because this sheds light on the algebra structure. Or why this? Yeah. By the way, if you forget about jet space, then it's clear why x and dx is a coordinate on C and d is a coordinate on the phi bar. So indeed, we have something like this. You have to think. I should have mentioned it there as well. So d, as you see, d n is like d dx minus n. So this interpretation of the notation equally applies to each of those remarks. Anyway, what's important is that this is a Poisson algebra. Now, there is an observation. I've seen it in one of Tomayuki's papers that if A is Poisson, then Jetson A is Poisson, as Bellins and Greenfield would say, vortex Poisson. It's not hard to prove. This is a very important observation. I would even say.
Before proving it, what does it mean?
Oh, I hadn't. That's a remark. I will come to that later. That's actually a point of item 2 in my abstract. This is where I would like to explain that. So, but I'll say a few hand-waving words. So. In hindsight, it's my personal opinion. A statement like that is, how to put it, raison d'etre, perhaps, of the whole theory. So I think it really belongs to this kind of philosophy, belongs to Beilinson and Drimfeld. It's that if you go from schemes to d-schemes, so from algebras to algebras with the action of algebras of differential operators, and this is exactly what's achieved by a passage A to A, and then an analog of, say, a Poisson algebra is not an infinite dimensional Poisson algebra, but something quite different, vortex Poisson. Similarly, an analog of Lie algebra is not a Lie algebra in infinite dimensions, but something different, vortex Lie algebra, sometimes people call it, or Lie star algebra, as BD called it. And this is something that I'm planning to explore in greater detail later. So, but at the moment, so this fact is that this fact is interpreted as a vortex algebra is really the quantization of a vortex Poisson algebra. Something that we achieved with usual algebras. Remember, differential operators were quantization of the algebra of functions on something like this. So now it is perhaps, where we're headed is perhaps clearer. Any questions?
So how do you relate the 2 points of view?
Which two? I don't know. They are different. It's a non-trivial question. I don't know an answer. Mayuki, do you? How is Kapranov-Vassero related to this? It's quite different. When I first told something like this to Misha Kapranov, he was interested, but he didn't elaborate. I think he didn't know. Maybe he knows now, but not a couple of years ago. I don't know. It's different. All right, so fate is not easy to escape. So a vortex algebra structure. I deliberated for hours on whether or not to give the definition of a vortex algebra. And I decided not to. I know this is a dereliction of duty. Tomoyuki told me that he didn't include vortex algebras into prerequisites. But I decided at my at own risk to do so. Instead, I will give you a few informal remarks, and I'll try to show how you actually carry out computations. It really is the genesis of this whole subject because it grew from physics so very recently. So we often know how to compute, but don't quite understand what is it that we are computing. So a few words about vortex algebras. I've been so slow, I won't have. So what's a vortex algebra? So on a more formal level, it's like Borches defined it. It's a vector space, a special element, vacuum vector, that plays the role of a unit. Derivation, I know. Del is so hugely overused that I don't like denoting the derivation. It's just a linear endomorphism. I don't like to call it T. We'll see soon why. And most importantly, a family of products. plus axioms. One thing I wanted to tell you is that what's important is that it is often convenient, and there are fundamental reasons behind that, that to each x one can associate a field. So it's a formal power series, infinite in both directions. That simply labels all, combines together all those operations. One reason that fields are important is that x is rather states. So this assignment of x of z to x can be easily inverted. That's one of the axioms. That is, if you take x of z and apply it to the vacuum vector, you will not get x. But what you will get will depend on only positive powers of z, and if you let it be 0, which I will informally denote like this, then you will come back to x. So this allows one, that's a very convenient device for a lecturer. Sometimes, instead of manipulating x's, manipulate the corresponding fields. What I really wanted to tell you is what is it that you actually need to define in order to define a vertex algebra structure. And I have an egotistical reason for doing so, because I'm facing the problem of describing such for beta gamma systems. So this is called, yeah, by the way, by way of apologizing. So if you really want to learn the definition, study your favorite textbook on vertex algebra. There are plenty of them. My personal favorite is Frankel Benzi. So what's called reconstruction theorem in that text, for example, just a reference. So what is it that, suppose you are given a V, what is it that you need to know in order to have a vertex algebra fixed? Well, these are less important pieces of data. What's important is a collection of fields. They're not coming at the moment from V. It is just a collection of fields of this type. I can be missing some of the conditions, but the fundamental conditions to make sure that those allow you to define the vertex algebra structure are as follows. First of all, they should be pairwise local. What that means is if you bracket any two of them as, coefficients or operators. So bracketing means formally computing brackets of those coefficients in front of the variables. Since there are two of them, and for each power of z times power of w, you will have just one commutator. So it makes perfect sense. It's a huge expression in w. It's not an algebra or anything, but what's important is that it's local, meaning that even if it's not 0, it's filled by sufficiently large power of z minus w. This happens. There's this famous delta function. That satisfies. You can compute and see that z minus w multiplied by this infinite expression is 0. That's one condition. And another is, I'll try to visit here, so this. Now is the time for this vector to play a row. So let me put alpha above. So then we will be getting coefficients. So what you can do is to take finite collections of such coefficients with non-positive, negative, strictly negative ends. So you can consider monomials like this: f alpha 1 minus n minus 1, f alpha 2 minus n 2, etc. Finitely many, but all of them applied to 1. If those linearly span the whole thing, the linear span of such elements must be the entire thing. Missing a couple of other conditions, less important, but of course important. The theorem is there is a unique vortex algebra structure on the space such that you can easily guess from one of the axioms. So if you pick your favorite f from there, say f alpha minus 1 applied to the vacuum, and the corresponding vector field will be precisely f alpha of 0. Make sense? Any questions? All right, armed with this, it's easy to handle this example. So we need a set of fields that generate the whole thing. From the vacuum. So the vacuum will be the unit in this polynomial ring, and we'll need only two fields. X of z will be the one that has already appeared. And there is, I'm sure, some importance in this coincidence, although at the moment, that's just a formal coincidence. That was a point in this space. We do a similar thing to D, except that there is a shift, mysterious, no doubt, for a beginner, a shift like that, so that using those standard notation, x with index in brackets is xn, and D with the index in brackets is not. It's the other way around. This is. This isn't. It's minus 1. Hazarded a guess. So the sum should be minus 1. That's, yeah, I guess then it works. Plus, it's impossible. You're never certain. But the sum of the indices must be minus 1, so that's the rule. Now, I don't have to tell you that this span condition is clearly satisfied. It's just a statement that the polynomials are multiplicatively spanned by x, by the variables. As to the locality, I have just two fields. Yeah, there is D. D should satisfy that bracket of D with a field, whatever it is, phi, is phi prime. This will immediately tell you how to define D acting on the space of polynomials. It will be an order 1, a linear vector field. It's easy to understand. In fact, in the later on, it will actually give us Virasoro algebra lying there. So locality. So if there are enthusiasts here, then they are advised to verify that the bracket of this, it's easy to compute, there will be either zeros or ones. So this is just the generating function of all those commutation relations, and the answer will be precisely the delta function I mentioned. And so times z minus w, this thing is 0. And this is more or less what one had to verify. So that's just an algebra. Our aim is to cook up a shift. You may answer why at all try to do that. I can explain to you historically how this occurred. It's a rather non-orthodox thing. Well, of course, for any algebraic structure, you may want to talk about shifts of such things, but why would one want to do with such a thing with the vertex algebra? Those many years ago, it was new. But anyway, let's not spend too much time on. I'll show you how this is applied, how this really related to geometry, and that will be a justification, if you will. So I want to get a shift. Now let me return to this picture. You see, what even do I mean by that? Well, the thing looks like a module over polynomial. So of course then, it's quite clear that given it, one wants to localize. That's just a symbol at the moment. What I mean is quite clear. I want to tensor that polynomial thing with the algebra of appropriate fractions, F, non-zero F. Here is this thing as a vector space. For this to make sense, we'll ask ourselves, is this a vortex algebra? The answer is, so what is it that we want, at least? We want to give ourselves the first question that arises. So we will use the same methodology. So I keep erasing this important picture that I will be referring to all along. So there is something here that we're not going to divide out no matter what. But that's a C of x naught mod. Now, in particular, it itself lives there at the zeroth level. So as a vector space, what we will get is the same thing, except that now, living here, I will have the localized thing. So the question to address, so of course, so we need to assign a field to H element. And of course, nothing has happened to D, so it will be dz. So the issue really is, give me a function. Formally, at the moment, it's an element of this space. But in fact, the only thing I need for the following, for the construction to follow, is that I will give myself G, a differentiable function. So I want to make sense out of, so I want to define this. Or, informally speaking, I want to log x of z into g. Yeah, so x of z is an infinite sum. It has a constant term, and then a bunch of non-constant terms. And what I suggest we do is we think of this as a small perturbation. And then define. That field to be the result of a formal application of the Tyler formula. So sum the nth derivative of g at x naught divided by n factorial times epsilon of z to the nth. It definitely makes sense. The result appears to be highly non-palatable, but it definitely makes sense as a collection of formal series with coefficients in operators operating on that module. So the reason it works is that, first of all xi's commute among themselves. And most importantly is that with a positive index, this operator is locally nilpotent. Locally nilpotent in all possible ways, with respect to raising powers and with respect to an infinite increase of this index. And this ensures that if you fix a power of z, then the corresponding expression will be extremely huge. But if you give yourself a minute to think about it, you will see that this huge expression makes perfect sense as an operator acting on that moment. The fact that this is bounded from above makes sure of that. You can always move all x's in such a way that the positive coefficients are on the right. You use this for that. And then you use this local nilpotence, and you will see how it works. So we've achieved, by the way, I don't remember how many times, including the referee and dear friends, I was pointed out that you cannot do the Tyler series expansion of any C-infinity function. You need convergence, they tell me. This is a totally irrelevant issue. A series doesn't converge in any sense of this word. But the only thing we need is that coefficients define an operator, and they do. So, all right. So, does this suffice? So it's quite clear that this collection of dz and, I don't know, g of x of z for g in the localization, or indeed you can even, as you see, we're starting seeing that you can work in any category you like, infinite, analytic. It's clear that these satisfy the spanning property. The crucial thing, of course, is the locality. I leave it for the students here to verify the following extremely nicely looking formula. G prime, like dx. G is a function of one variable, differentiate it. Make the substitution and multiply by the delta function. That's the result. So that's an exercise. Thank you. So the reason is, so if you're not too familiar with this, practice with, it's a very simple particular case of the weak theorem. So you can start by bracketing D with, a polynomial function. And then it's quite standard. Once you have this, another thing would be to realize that the definition of x of w agrees, given here, agrees with the one we started with. So after you've got this, and this is pretty standard, this won't surprise at all. So a vertex. So by the way, I forgot to mention it. I skipped some of the axioms, and then, but you may wonder what. So x of z is attached to x naught. How about x minus 1? This is important for what goes, for what follows. So x minus 1 is the image of x naught under D, and one of the axioms I skipped implies that x minus 1 of z is then simply the derivative. If you further go down in terms of this index, you will be getting further derivatives, perhaps divided by corresponding factorial. So read this as that text for the details. All right, so it is clearly a chiffon seed. We have achieved a very modest achievement is rather modest, but it is. So we've got a chiffon seed. What's the point? Some of you may wonder. So now things will start getting more interesting. So remember, I spent much time on doing CP1, and now you see the reason. Because now we will try to cook up a Shiva Vortex Algebra on CP1. The logic is rather clear, of course. We have two charts. And so for each we have Vortex Algebra. Or rather Schiffer Vortex Algebra. So now we would like to consider an intersection. Where we have two copies of similarly looking objects. D chiral C of to be conscientious, I should have written like brackets and then x inverse. I will simplify the notation. But what I mean is, to be clear, or a similar thing in terms of y. They are, of course, isomorphic by replacing x and y, but that's not what we need. So what we want is to lift the relations that hold classically on the intersection. X is y inverse, and dx is minus y squared dy. So what we want is lift those to an automorphism, to an isomorphism of the two algebras. That make sense? And here is when the fun begins. So we have, standing next to each other two copies of each other. So we have x inverse on top in one, and y inverse on top of the other. Of course, to begin with, we naive simply say that x would be identified with, well, rather x naught with y naught inverse. Or perhaps even more tellingly, but also more informally, I will identify the field x of z with the field y of z inverse. Y of z inverse, of course, it means is y inverse of z. Something I just explained. Now there is x minus. If we know what happens to x minus 1 is predetermined. It's the result of the action of d, and d must be preserved. So that's very easy, and I'll leave it out. The question is what to do with d minus. I don't have room for y. Let me put tilde. Tilde means d for this y. Right? So, this is all informal. We are trying to work our way through. So the only thing that comes to mind, of course, at least comes to mind first, is to send d minus 1 to y naught squared d minus 1 tilde. Simply mimicking that formula. If you think about it, you could perhaps, so we're trying to make this transform as if it were an actual ddx. Well, we can say that there is some discrepancy of the indices. Does this all make sense? Well, here is a more convincing point of view. I told you that elements are the same as fields. To say this, if you give this a thought, you will see that to say this is quite the same as saying that the field goes to that's more convincing, isn't it? But there is a subtlety there, and people who have experience in Vortex Algebra should see it. What is it? Does writing like this just make sense? Can you multiply such infinite series? The whole difficulty of the subject is that if you think in terms of such series, they're infinite in both directions, and it's not clear at all that you can multiply them. There is this famous operator. So if you have two fields, whatever your vertex algebra is, this one is perhaps. A product like this doesn't always make sense. You can kind of regularize it by putting two dots. And that means moving all the operators in each monomial, moving the all 8 with positive, non-negative indices to the right. And that makes sense of this product. Again, this is something that I'll skip writing as I'm pressed for time. That's a degree 3 expression. So you have to make choices, and you will later on see that the way you make a choice doesn't really matter, because there is a fundamental cohomological problem underlying this. So many choices, and you have somehow to make all of them and then choose the one that works. So the standard way, and that's where we will start, is to write it like this, which means doing it, nesting them from right to left. So given 2 fields y and d, first form this, I have a third one. And I multiply this with this, like that. So that's what the notation like this means. All right. I guess, or maybe not. Maybe let's spend another few minutes and then make a break. The question is, will this work? What is it that's supposed to work after all? That's what the beginner is expected to ask himself. Well, at least commutation relations, and a little knowledge of vortex algebra theory will show you that this suffices. So a field commutes with itself. It's not always so, but it is in this case, thanks to the definition of my algebra. And then there is more subtle issue. This is, we know what. So the question would be, is the image y squared d with what? That goes there, and that goes to y inverse. This is easily seen to be true. All computations I miss will tend to be simple and instructive exercises. So this is patently. So this. So we need what? Y inverse 0. That's patently correct. It's made out of y's. Y's compute with themselves. So the whole point, somewhat unexpectedly, is this benignly looking equality. So what we have to check is y squared d. We want this to be 0. It's not obvious because some d's here and some y's there. They don't compute. So something is to be checked. I'm just thinking what form to give you the answer. So the point is that this is not going to work. That's not 0. The answer is something that involves actually what you will actually do if you carefully compute. It's not very easy. So it really is an exercise on the weak theorem. So what people who want to practice with this should really learn the famous computational device here called the weak theorem that allows you precisely to compute such expressions. But in a different form, though. So the convenient language is that of OPEs, closely related to what I use. I'll just write down the answer. That's the best I can do. So what you will get will contain a couple of terms like this. So it didn't work. And the question at that moment of time, those years ago, what is one supposed to do? Is the project dead? I'll give you the answer. The discovery was that so this suggested, oh, is there somebody else outside? We can wait more. So we begin. So what was then discovered is if this suggested but failing transformation rule is adjusted by adding this correction so where did all of this start? Then, that's a very simple computation. You will have to see how this interacts with this one and this term with this one. You know, D hits Y and creates a thing like that. So people have at least some experience working with it. Of course, I don't have time to show you the actual computation on the board, to say nothing of the fact that the chance of my getting quite right is 0. So what will happen is that 2 more terms will appear, and they will kill those, and you will get a 0. It's easy to understand that the rest of the computation won't be affected. So here is then the result. First, the map that sends x0 to y0 inverse and d to y0 squared d tilde minus 1 plus. Yv prime is the field. This field, as follows from the axioms, is the one attached to, no, minus 1. Extends absolutely uniquely to an isomorphism of the 2 vertex algebras. of, yeah, there is. Yeah, for that computation, I was allowed to change the overall sign, but here, of course, it's like that. So an isomorphism of these algebras. And second, we could as well go backwards. Of course, it should work. The analogous map isomorphism. Of course. Like, why not those inverse, etc. Is the inverse of the previous one. In principle, it didn't have to. We should have used the inverse of the first one if this happened not to be the inverse, which is a very strange thing to happen, if at all. But it doesn't. And so, be it as it may, the result is then we've got we will soon see that it's unique in a sense. But anyway, we've got a first example of an algebra of chiral differential operators. Yes?
So how does one see that this is the right thing? How does one,
How
does one guess this correction?
Oh, that's what I tried to explain. How one gets this correction. First of all, this particular, well, I'll tell you. This particular one, let me tell you about this particular one, but the fact that the correction is needed is kind of built in the whole theory. This is all because fields cannot be multiplied. For some reasons, this famous operation of normal ordering is important, but that's a computational, essentially computational tool. If you do something else, if you, for example, multiply dw by this product and only then do the normal ordering, you will get something different. But what can you get in principle? I'm back to this picture. So we will later on see that a representation of this level as a direct sum of two cy naught modules is not natural. This naturally is a submodule. And the whole thing is, so there is a submodule and there is a quotient generated by this thing. So whatever you do, things are not naturally determined by the symbol. So in a situation like, it's cohomological algebra, so work has to be done, and sometimes you're doomed. Sometimes this is even impossible, depending on what you want to achieve. So that's a general remark. What can you add in principle? Well, y minus 1 times something. So this is, but in fact, there is an extremely, I missed it too, haven't I? Should get to. I could have guessed this formula within a few minutes, if not, how did Dyson call it? Compartmentalization of the brain. What really helps is that this particular formula occurred in a different but closely related area of math. And this is something that really will be the subject of discussion today in a few minutes. So you'll get, let's say, a more satisfactory answer perhaps in a few minutes. All right, we've got our shift. So let's play with that. So analyzing so the first thing to understand is that it is not, we like, in geometry, we like having, quasi-coherent, perhaps coherent shapes, but at least shapes of modules. This is not. But it is not, so that's bad news. The good news is not far off. So let me explain what I mean. Remember I told you that the fact that locally the space of sections is a modulo over functions is misleading. So let me return to what the shift looks like. The first floor, the second, etc. You can, of course, multiply by x0. And of course, we think of x0 as functions. And by the way, if you look at things on the first floor, and they transform the right way. So this is naturally part of the structure shift. This is for the reason that the corresponding field commutes with itself. Transformation law is x goes to 1 on x, and so it's exactly like the actual function. So there is no difference. Furthermore, even this part is an homage. So this also is an homage. Can you guess? Hint. X minus 1 is a certain derivation applied to the function x. Sounds like a one form, and it is. So this naturally is the space of sections of one forms over C. Just study the transformation. I told you everything that's needed. You will see that. So informally, x minus 1 will go to y0 inverse y minus 1. Yes, so x minus 1 is naturally dx, but it's even. That's the criminal. So the problem here is that the vortex algebra, so one way to think about it, so fact that is easy to verify, and that's an access. Again, a very simple access. On computations in this simple vortex algebra, simple in, plain English sense of this word, and this rather simple vortex algebra. So suppose you have d minus 1, and suppose you multiply it by x0. Of course, so I'm trying to convince you that the natural operation of our module structure actually fails. It's not natural. Were it natural, this element would go to what? The image of y0, of x0, which is y0 inverse, times, well, this whole expression in terms of d. And that's false. The reason what is that's correct? What's built in the construction is that the normal ordering product, it's part of the structure of the algebra, is preserved. So this will go to y of the inverse times, well, the image of y squared d plus 2y prime. The meaning of it is, of course, that it's irrelevant, because this field I'm just trying to make a connection to more standard computation, but you start with this field and then you multiply this whole thing. That's what I'm trying to make sense of by this one. So you put those dots manipulating these two fields. So finally, all of it. So this is true, but this is different. This field is not the one that is attached to that element. And the essence of the story really is, it's somewhat a different computation, but closely related. It's that the normal ordering product operation is not associative. If you multiply like this, the result is different from if you multiply it like this. So such computations are must-do exercises for people who would like to learn the subject, or even more generally, the subject of vortex algebras. These elements are only valid, these equalities are only valid modulo terms like that. So if you compare this with this, you will get as a correction a bunch of terms that already have been used as a correction. There will be, the difference will be long, so difference between the two, they will be equal modulo this submodule, but there will be a difference, and that will be an element of what I denoted by identified with the one force. Yes?
I'm just having trouble understanding the difference between the two on the right-hand side.
Yeah, I can understand. You can't imagine how much pain it was to figure all of this. I mean, each such equality probably cost me a couple of years of my life. Yeah, but they are different. What you have to do is you write y of the inverse and multiply by it. Y of the inverse is a huge expression. So modulo some terms, you will get the same thing. It's just y will go out. So modulo things that contain y only without d will be this same yd here and there. When y goes away, so modulo such terms, it will be yd in both cases. But there will be correction and there will be different in each.
The culprit is y squared d, or the culprit is, you're saying the culprit is y the inverse. So, it's the term with y squared d that we can have ambiguity. And which order you take.
But I already made a choice, so I no longer have any ambiguity. Now everything is fixed. You just compute two well-defined expressions, and you observe that they are different. They are the same modulo y's, modulo the module of one force. But otherwise, the difference will be a certain 1/4, non-zero. It's just the computation I started with. Why is it that y squared d doesn't satisfy the correct commutation relation? It does modulo terms that involve y only. It's a similar computation. This is the reason why vortex algebra is in no way an associative algebra.
Oh, y squared d versus y yd.
That was a choice, yes. Yeah. In this case, well, here there is no choice. I mean, they commute. If you write it like this, this is, oh, d minus 1, right? But the corresponding field is indeed like this. That's part of the axiom, or perhaps a theorem in vortex algebra. And that's different from y squared times. So this exercise is similar. It's not, this exercise doesn't imply that, but that's the reason why they're different.
So some of this just back to the old calculation, saying that the field of the inverse is not just dividing by y naught. Right?
Yeah, exactly. Yeah, you can put it this way. Exactly right. It's not just dividing by y naught. All right. So it's not a shift of all modules, but a computation like this, if you do it carefully and look at more complicated terms, will convince you, even though this is not a shift of all modules, And I'm continuing my sentence, if you will. So it's not far off, I said. So precisely, it carries a filtration that preserves the grading. The grading is this one, 0, 1, 2. So that the corresponding graded sheaf is, in fact, each component I should have denoted like that. So I said that we've defined the sheaf. In fact, we defined it in such a way that it is a direct sum of subsheaves. And so this n is exactly 0, 1, 2, etc. So n is given by discounting the sum of subindices. Come back. So in fact, each homogeneous component, in fact, I can even write it now. In fact, for any n gr of d chiral CP1 n is a locally free, free finite rank sheaf. I will show you exactly what it is. So it took me so much time, but here is the picture that will tell the whole story. I already started telling you this story. So the upper level is the structure sheaf. The first level, it contains one forms. And the quotient, of course, remember how D transformed. Modulo, that was built in our definition. Modulo one forms, it's vector fields. The rules of the game are very simple. Locally, an element is the product of the bunch of x's and a bunch of dells. Yes. So each x, no matter what index is, x naught is not included. So these are all positive. 0 gives me a function. I ignore those. So this is a basis over functions locally. So each x gives, you can easily guess, a one form. And HD gives vector fields. So for example, on the next level, you will have a bunch. X minus 1 squared, x minus 1, d minus 1, and then these themselves, d minus 1 squared, d minus 2, quite a few of them. So omega squared, but in this particular case, not even squared, squared. Well, not even, it's a symmetric square. But in this case, it's a invertible shift, so it doesn't matter. It will be, I could use O's. O minus 2, and this is O minus 4, etc. This will be O2, and this will be O4. So that's what the shift looks like. An exercise will be, do it carefully. Define this filtration and prove what I informally explained here. In fact, here is what you have to convince yourselves of. In fact, there is a formula for GR, a formula of the type that John used during his first talk. So what? There will be a bunch of forms and a bunch of vector fields and tensor products thereof, and direct sums thereof. And here is a generating function for that. Is this how you did it? And you worked in a, you had fermions. That was responsible for lambdas. I will come to that. And in this case, the situation is purely even. There aren't any anti-commuting things. So the whole thing is a sums of tensor products of symmetric powers of vector fields. Why symmetric powers? For example, if you take d minus 2 and square it, d minus 1 gives you vector fields, and the square will give you the symmetric, not tensor power of vector fields. Now, of course, in this, there is a reason why it's not a typo. There is a reason why I wrote x instead of P1. In the case of P1, this famous formula, I'm running out of time. Permit me not to explain what that means. I let John explain if you ask him. The point I'm now making is that this formula is ridiculously simple in the case of P1 because all these are one-dimensional vector bundles. So symmetric, this doesn't, it's not interesting. But if the dimension is greater, so we will, of course, discuss, and it's easy already for you perhaps to start discussing in your mind, the case when instead of just one coordinate x, there are several, x1, x2, etc. Then indeed, you will be getting honest symmetric powers. Agreed? Now, why I'm talking about it? Here is one of the applications of all this discussion that perhaps also attracted some attention to this subject. You see, you can compute, it's a nice shift, you can compute its Euler character. So if you have just one individual, let me write x just to hint that it in principle works for any for other x's. So for any shift, the Euler character is, you know, an alternating sum of, so one concept, sorry, I should have said this before. So this particular fact immediately implies that the cohomology with coefficients in this shift are all finite dimensional. there are only I is either 0 or 1 in this case, but, because the dimension is 1. But each of them is one dimension. Each of them is at each level. Each of them is finite dimensional. Why? Of course, there is this famous theorems in algebraic geometry about such thing, but this is not a null module. However, there is a spectral sequence, and each component like this has a finite dimensional cohomology. So the actual cohomology will be finite dimensional. If so, you can compute the cohomology of each component. But there are many components, and this is taken care of by this formal variable q. So in any case, you will get another character of the whole thing. It will be some formal power series in Q. This n will have to do with n appearing there. For me, that's the definition of an elliptic genus. In fact, this is essentially, I forgot, and it's not my purpose to lecture on it. I don't really know this subject. So it either is on the nose or closely related to the Witten elliptic Witten index. There is a paper by Castella that discusses such things in great detail. Maybe not exactly the Witten index, but perhaps it equals Witten index modulo a factor that's independent of the manifold or something like this. So if you do it for an arbitrary s, then the shift will produce you the elliptic genus. We will later on see that a shift like that exists if and only if CH2 of something is 0, and that guarantees certain extra nice properties of the Witten index. So there is a story there. That's my little advertisement. But what's interesting is that so think of this as the definition of a Witten index. But of course, the point is that Euler characteristic of a shift equals the Euler characteristic of the graded shift, and therefore, one reason there is something interesting about this shift of vertex algebras is that its Euler character is a Witten index. And since this is a shift of vertex algebra, it is potentially is actually related to some physics. So this is one of the reasons this subject may be of some interest. Any questions? Now I'm about to give another answer to John's question. By I and Vadik Shachman, with whom we worked on all this, I'm afraid even to think how many years ago, is that it is closely related to representation theory.
Yeah, my question was that's the wrong one to ask now. But somehow, if you want to generalize this, then the real question that appears is how to lift the action of the automorphism to an open subset.
Exactly.
Are you trying to explain that?
Yeah, that's where we're headed. Yeah. But I just want to show you some nice results. Why would we care about such things? I mean, we succeeded in this particular case. That really is, that's the point. You're absolutely right. But before discussing the general case, I want to discuss this example because it's not yet exhausted. So, there is a vortex algebra attached to SL2 hat. Do I have to remind you what SL2 hat is? Probably not. So, it's a central extension of all depends on your point of view, whether or not you want to complete, but it's not very important for my present purposes. So it's a central extension of the loop algebra, and that's the center. And when talking about modules, you typically specify the number by which the center acts, and that's called central charge. So that's what happens. Level. So a typical SL2 hat module is the while module. Give me a second. I'll soon go down to a concrete while module. But in principle, you can induce. So this has a subalgebra of holomorphic loops along with the center. All this, I don't know. I think that's how I denote it. Perhaps I'm not sure, like this, or perhaps like this. I denoted an infinite dimensional G-hat module with highest weight lambda, where this acts by essentially evaluating at 0, and K is the level. Of those, the most important for our purposes is the vacuum representation, one that has to do with lambda equal to 0. Usually denoted like this, or at least often denoted like this. Something like this. The point being that this is not just an SL2 hat module, this is a Vortex Algebra. Famous work of Frankel and Joe. And it is generated by the methodology I hinted at by 3 fields. Of course, I'm committing abuse of notation. I mean, not so much E as rather the way each EI acts. So I should have perhaps written a row of E or something like this. But in any case, we have these 3 fields that generate this Vortex Algebra. I'm doing this only by way of reminding you how this algebra is defined. The point I want to make, perhaps you have already guessed. So, lem, send the field E of Z to G of Z, and the field F of Z to minus x squared D of Z, of course, the dots, minus 2 x of Z prime. Well, E of Z and so that, of course, determines where H goes. How? Because of the statement. So the lem, the assignment that sends E to this and F to this, defines a Vortex Algebra morphism. DSL2 minus 2 2, well, just look at the notation. Of course, I meant the space of sections of my sheet on the corresponding chart. Furthermore, no, that's not what. Right, but I'm being too conscientious, then I should have. Furthermore, this map factors through the inclusion of this space into the space of global sections. So actually, this is a embedding into the space of global sections, which gives an SL2 hat structure of the whole sheaf. I haven't answered John's question. Actually, I have, but if you know that. Do you see that I have answered your question? These are famous formulas. They are perhaps way more important than anything I've been able to tell you today. So if you forget about all this geometry flying around, if you simply take a beta gamma system with this funny notation D and X, that's just the famous Wakimoto definition, the famous groundbreaking definition of made by Wakimoto of what later on by Fedor and Frankel was called the Wakimoto module. So, and that's how you could easily guess this formula. This, on the surface of it, has nothing to do with gluing. But a formula like that had already been classic at the time we were working at. So if the brain wasn't compartmentalized, we could have guessed right away this. And this is exactly the same term. And this, of course, is what. So the whole point of my computation was that this is a field that extends to a global field. That's how the shift was defined.
So the arrow is opposite the right brain.
The arrow is the opposite. It's hard to disagree. Otherwise, it would make sense talking about factoring. Life would be so much easier. All right. Once we have this, so that of course shows one that perhaps we are onto something. But be it as it may, let me keep that expression up there. Fine. So we have a shape. It's acted upon by SL2 hat. Question: what is it as an SL2 hat module? There is something I haven't. Well, it follows, of course, from the formula. There is this, -2 there. So for people unfamiliar with the subject, it's just a number, but for experts, it's one of the more famous numbers attached to SL2. -2 is exactly the level when the universal enveloping algebra develops a huge center. So it's the critical level. And again, a hand-on exercise here for the students would be, remember, EF plus FE plus half of H squared was central. If you go over to the fields, you have to do the normal ordering. This may cause trouble, and in general, it's not going to be a center. But the exercise is under the map there. This thing goes, to believe it or not, no, it goes Is it minus? No, excuse me, to 0, of course. And this can only happen when this is central in the representation. And there is a, well, the fact that the center is -2, of course, immediately follows if you start verifying this result. So a proof is left out. It's just a computation that these two fields satisfy the required commutation relation. In particular, this field commutes with itself. And that's what we did when we did the gluing. So if you do that in particular, you will, of course, see that you'll get the formula for H, and you will see that the level is critical. And in particular, this whole thing goes to 0. It may only happen that this element is central, and it is at this critical level. All right, so we are working at the critical level. So, another result. So you see, it's abstract nonsense from all category theory that if you look at, you are doing category, the O category for SL2 at the critical level, but you also have to work with, so to say, Cardan-Lustig version of this, the one where SL2 acts in an integrable fashion, so that each module is actually a module of the corresponding finite dimensional group. So, and the while module is a typical example there, in particular this one. And an arbitrary module is, so, but a while module, as any such module, has a unique maximally reducible submodule. And there is an irreducible submodule and unique. And so there is a corresponding irreducible. And that's a theorem that, in the case of SL2, so was easy to establish all those years ago for SL2. So lemma. The space of global sections is precisely that, irreducible. How about H1? It's isomorphic. I will now show you how one can prove this, because it's great fun, I find it. So the idea is very simple. We know H0, we want H1. If you look at the definition, an explicit computation of H1 is next to impossible. So you really need to use representation theory and whatnot. In this particular case, it's very easy. You can do, you know, whenever you have, I did it on more than one occasion. Whenever you have a graded vector space, then you can consider its character. So I can take, therefore, the character of H0 and subtract the character of H1. So that's what I, a few minutes ago, called the Euler character of the shape. Oh, but we know what that is. It's the Euler character of the sheaf lifted there, written there. It was a very nice combinatorial exercise. So I'm saying that the Euler character of this sheaf is I think I remember it, but I just don't want to take chances. So exercises to prove that the Euler character of this sheaf is the product 1 minus q to the nth to the minus 2. You know what it means. You expand out using the geometric series and then multiply out the terms, collect the like ones, and for each power there will be only finitely many contributions. You'll get something like so what does the computation amount to in order to get this result? This is a simple, a nice combinatorial argument based on on how we arrived to this formula. Remember what we obtained? We had a structure sheaf on top. What's the Euler character of the structure sheaf? Well, it's P1, for God's sake, so it's 1. The next level was, omega and t. Omega is O minus 2, and t is O2. If I'm not terribly mistaken, the Euler characteristic of On is n. So let's see here. This one we considered. It's a three-dimensional SL2 module as far as global sections go, and H1 is 0, so it's 3. So I guess the formula is this. For example, for minus 2, so this is 3, and for minus no global sections, of course, but 1 H1, so minus 1, as this formula suggests. So you would have then 2q. You can play with this, and you will. So at the next level, you have x minus 1 squared, x minus 2, and so it goes. X and dels are kind of symmetric. Not kind of, actually symmetric. And then you compute. So remember what it was. It was 2 times 2, so 4. For example, this. That's simply O minus 2. And that's O minus 4. And you can compute. That will give you 5. That will give you minus 1. That will give you minus 3. I think it was 5. So that's perhaps one of the more pleasing exercises that I've been able to give you. You should be able to figure out the pattern, and then you will get the decomposition. What's the point? Well, look. So the result is this. That is subject to, so this is my unknown. That's the SL2 reducible at the critical level. It's easy to write a character formula. I think it's something like this. I can check it if you like. Yes, that's what I have in my notes at least. And so now we are back to what? Middle school. This thing is that minus that. And if you do, if I did everything right for H1, you will have not quite this, but Q times this. So it's the same formula, but for some reason shifted by Q. I will explain it. First of all, if you have, in this situation, it's quite clear that an irreducible is unique if it's a reduced. An irreducible is completely determined by its character formula, except that typically here the shift by Q is allowed. It's like renaming, changing the gradation. So it already proves that as L2 hat modules, they are equivalent. But one wonders, why is this shift? And this is also easy to understand. So these are all highest weight modules. So for each node, its global section, of course, it's generated by 1. There's no doubt about it. It's a Vortex Algebra. It's vacuum vector. So the corresponding V of SL2, of course, sends the vacuum to 1. So that's where, and of course, it lives in conformal weight 0. So that agrees with the formula for H naught, which didn't contain Q. How about H1? In conformal weight 0, well, H1 comes from O. Well, conformal weight 0 comes from O. Of course, there is no contribution to H1 there. So the contribution for H1 comes from conformal weight 1 component. And that, of course, that's what follows from Q. So what's H1 of that component? It is made out of one forms and vector fields. It's quite easy to understand that what lives here is H1 of omega, same as O minus 2. And this is something we have already discussed. Remember under what circumstances? When we were talking about completely different subject, twisting differential operators on CP1. In any case, this is one-dimensional, and it is spanned by that form. So this is it. So if the whole thing is an irreducible L2 hat module, it must be generated by this vector. And of course, it lives in weight 1, and therefore the formula makes sense. Any questions? I'm curious, how long will you be willing to tolerate me? I know how easy it is to lecture. It's a totally different matter to listen. I have 10 more minutes. If you allow me, I will continue, but I don't want to take my rights too far. Shall I? Yeah.
If we replace CP1 with CPN?
Doesn't exist. That perhaps is the most intriguing part of this story. Such sheaves pick the second component of the Euler character. Such a sheaf exists if and only if CH2 of cotangent bundle is 0. You already, it's essentially an abstraction problem, looking for those corrections. In this case, we were able to go through. And in the case of PN, this is plain impossible. For the flag manifold, this is possible, and the answer is simple. This is our work with Mayuki. So for G mod out B, the space of global sections is still the irreducible vacuum representation at the critical level. Mm-hmm. Well, no, for any simple algebra.
G mod, you're talking about G mod B phase.
Yeah, exactly. G mod B.
Wakimoto,
Wakimoto, it's not. Yeah, it's a working motor module, restricted, right? Restricted working motor at, so on the globe, on the big cell. Working motor is something that's, that lives on the big cell, and the reducible is a submodule.
Global section is you have you fit all levels at once. H0, H1.
Yeah. So it's each HI will be a direct sum, right? And not unique. It's the number of elements in the while group. Before I move on, so just so you see, at least part of my task has been accomplished. So we now are equipped to compare the two theories. So all of this is very much like a Beilinson-Bernstein localization on CP1 only. And there the situation was extremely favorable. We had a functor from D modules to G modules, and if we don't twist at the zero level, and it was an equivalence of categories. In particular, you see the functor in one direction was the good old functor of global sections. I think it formally follows from the fact that this is an equivalence, but be it as it may, it's a fundamental part of the proof that, of the statement that the higher homology all vanish. That's the reason why they called this particular variety, as well as any, the same is valid for any flag manifold. They call it DFI, because that's the characteristic feature of similar results with D replaced with O is the characteristic feature of a fine manifold. So in this sense, this is DFI. Our situation is, whether this is good or bad is of course a matter of taste, but personal taste. But in this case, that's different. So we have a, well, not that I don't want to talk even about it, but what we, informally speaking, I don't want to. Yeah, there is a functor like that does exist, of course. What I explained is that, of course, there is a functor of global sections from modules over this sheaf, Vortex Algebra, to G hat at the critical level. And it can be an equivalence, because in this case, you see H1 of the thing itself is non-zero. So this functor is not exact. All right, now so I'll try to explain the general theory that underlies all of this. But let me finish with such nice, concrete manipulations. Another example. So Chiral the realm on I don't have much time, but I think now it's very easy to explain another very attractive such computation. So let's play the same game in a super situation. So let me remember what it looked like previously. It all had to do with jets in cotangent bundle. If you forget about jets, it's cotangent bundle functions. There are, X and D And we go to jets and we get all those indices. So now, let's do the following. Let's enlarge C, but in the odd direction. So let's do the tangent bundle to C, but require that the coordinate in the bundled direction is odd. So that's pi. So that's what habitually is called pi tx. So it's tc, it's a two-dimensional. This thing would be simply C2, but now you write it as C cross C, and you declare this C odd. So here you would have two coordinates, and here you would have also two coordinates, but another coordinate would be phi. Since this is t, I would think of phi as dx. We have already seen dx. This dx will be declared odd. So if you, for this, writing like this perhaps only obscures the matter, but later on will be very helpful. So just a flat space with two coordinates, x and phi. I'm writing phi even though its meaning is dx to stress that this is even. Now let's play all this game. Yeah, so give me a second. So this is our Superman. So this is a replacement for C. Now I will do T star of all of this. That, of course, amounts to adding D and d phi. My letters multiply, so I'll make my life somewhat easier by simply calling it psi. So I have X and D. And now I go to the jets and start playing all this game. So the end of this would be what they call beta gamma, and that's what comes from there if I add indices. MBC, you see, it's extremely imaginative physics notation. Just look at the letters and call the thing by simply listing the letters. So BC, beta gamma system. Physicists call those beta and gamma, and these B and C system. So it's like what we had previously. At level 0, we would have x naught, but now we, in addition, have phi naught. Level 1, just as before, x1, d. Here, similarly, there would be f minus 1. It's made out of phi naught by this Vortex Algebra derivation, del. But then there will be also psi minus, and so it will go. So we will get, the relations are similar. So phi and psi commute like just like those two fellows to give delta of z minus w, except that these both are even, odd. So this bracket is an anti-bracket. So we get an algebra. Not only it's conformally graded, but now it's also graded by fermionic charges. Here you have lots of possibilities. For example, you can assign this degree. I want to think of this as dx. And if you want to keep the gradation as that of the usual de Rham complex, then this extra grading will give 1 to phi and minus 1 to psi. And so we want to get a similar shift, which is hopefully graded, filtered, so we want d chiral, but not, let me rather write the corresponding, yeah, so previously it was what? we started with C. So in this case, it would be instead of C, pi, CC. That is easy to construct. That's this guy. Now we want to take two copies like this and get d chiral pi t CP1. If we are able to construct it, we will call it the chiral Durham complex. Why call it like this? Well, just because, just as previously degree 0 contained only functions, here the degree 0 will contain the usual Durham, x and dx. Make sense? Now it's a race against time. So here is what happens. I've explained everything so carefully, I hope. Now it's very easy. So, but now we have two copies of this. Pi TC and pi TC. So, x phi x tilde phi tilde d psi d tilde psi tilde. How do they transform classically in the ordinary case? Just that manifold pi t p1. Well, this has essentially been used. So x goes to x tilde inverse. So for example, phi is identified with what? X tilde to minus 2. Let me write y. Y minus 2 phi tilde. Psi is dual, so that will go to y squared psi tilde. This is something that we have used in the odd situation as well. So of course the whole point is what happens to d. D goes to minus y squared d. All right, nobody leaves the room before you give me the answer to the question. Is this reasonable? Forget about the vortex algebra stuff. Is this reasonable even ordinarily, classically?
You should kill this.
Hmm?
You should kill all the quantities.
Yeah. It's I have a competitor. Look at our guest. So, chain rule. That's outrageously wrong. The chain rule should give you what? d dx goes to d dx tilde d dx, and I've got this term, but there should also be d phi, so d phi tilde, so d phi tilde d dx. And that's another term. And if you compute it carefully, you will have something like 2y phi tilde psi tilde. Last trace. And that's the miracle I wanted to talk about. So, really last sentences. Now go to the chiral situation. What do you do? Well, you just postulate that these are fields. And we're well aware that this thing is very unlikely to work. But the miracle is that it does. It's like a thunderbolt. You compute again and you don't believe your eyes, but it does work. So this gives you, on the nose, so one, an automorphism, so x inverse to d y inverse, by simply postulating the classical formulas. And so that gives you immediately very easily defined the Durham complex on CP1. I'll spend some time talking about the Durham complex next time, and then I'll try to explain what does all of this mean. Thank you.
Can you comment on the question? So including the fermions fixes this problem and this one.
Yeah. This works. So the remarkable thing is that this is universal. You give me an arbitrary smooth variety, and I will define for you a Chiral Differential. And this is natural. It's kind of, I guess, I don't know what the highbrow terminology, but kind of defines your sheaf on the category of manifolds in a tau topology or something like that.